So the next statement, it states that if in a complex coordination number is 3, that means there are 3 ligands attached to the metal atom. The structure is trigonal planar, and then the complex will have no geometrical and no optical isomers. So this is your trigonal planar molecule with a coordination number of 3. This is the central metal atom, the black one, and the white ones are the ligands. Now, as I said, or as the slide said in our previous videos, we know that the bond angle, there must be at least 2 different bond angles for geometrical isomerism to be present. Between these 2 ligands, the bond angle is 180 degree. Between these 2 ligands, the bond angle is 120 degree. Between these 2 ligands, the bond angle is 120 degree. Between these 2 ligands, the bond angle is 120 degree. Between these 2 ligands, the bond angle is 120 degree. There is only one bond angle present and it's not even 180 degree. So geometrical isomerism is going to be absent. Now optical isomerism. We have already done the plane of symmetry with this molecule. You know it contains a plane of symmetry, okay? And not just one, it contains this also, it contains this also, right? So it contains a plane of symmetry, that is why it is going to be optically inactive, that is why it is not going to have any optical isomers. Even if all the ligands were different, okay? That is, this was a different ligand, this was a different ligand, and this was a different ligand. Then if I take this as the plane of symmetry, then it cannot be classified as a plane of symmetry because these two will be bisected, but then this ligand and this ligand will not mirror each other because they will be different, okay? That plane of symmetry will not exist. But which plane of symmetry will exist? This plane of symmetry is still going to exist if all the ligands are different, because that is still going to bisect all the ligands equally into halves, okay, and it will make mirror images of all the ligands, that is the top half will be equal to the bottom half. So you can say that the trigonal planar, if the coordination number is 3 and the structure is trigonal planar, then there will be no geometrical isomers and there will be no optical isomers present either. Okay, so now we come to the next point. In a complex, if the coordination number is 4 and the geometry is tetrahedral, there will be no geometrical isomers. This is a tetrahedral molecule. Okay, coordination number is 4. To the central metal atom, there are 4 ligands attached in a tetrahedral fashion. What was the criteria for geometrical isomerism? The criteria was that there should be at least 2 different bond angles present, one of which must be 180 degree. This is a tetrahedral angle, 109 degrees 28 minutes, 109 degree 28 minutes, 109 degree 28 minutes, 109 degree 28 minutes. All of the bond angles are same. There are no 2 different bond angles and even one of them are not 180 degrees. So this is not going to show geometrical isomerism. Whether it's going to show optical isomerism or not, we'll see in our coming slides. So the next statement, it states that if there is a tetrahedral complex and all of the 4 ligands attached to the central metal atom are different, then that tetrahedral complex is going to be optically active. Okay, now look at this tetrahedral complex and imagine that all of the ligands are different. Okay, just imagine all of the ligands are different. Now if you put a plane of symmetry from there, okay, so you are putting the plane of symmetry from there, you are bisecting this atom and this atom. So their mirror images are going to be equal to each other, that is this side of this atom will be equal to this side of this atom. But these 2 ligands, they are not going to be mirror images of each other because they are different, right? So if you put a plane like this, it will not function as an actual mirror because these will be different, so they will not be mirror images of each other. Similarly, if you put a plane from this side, that is, this is the plane, okay, this is the plane, it's going through this and it is coming out from here. So this plane, according to this plane, this and this are now not going to be, this and this are not going to be mirror images of each other. If I put this plane, then this plane will bisect this atom and this atom. But these 2 are still not going to be mirror images of each other because they are different. So, tetrahedral complexes in which all of the 4 ligands are different do not possess a plane of symmetry, and because they do not possess a plane of symmetry, that is why they are optically active. So, the tetrahedral complexes which contain bidentate ligands, okay, so the ligands which have a denticity of 2, which have 2 donor atoms, those tetrahedral complexes will be optically active because the rings which are formed will lack a plane of symmetry. There is an example. This is a tetrahedral complex. Now, because I have drawn it on a 2-dimensional sheet of paper or a 2-dimensional sheet, it looks like they have a plane of symmetry. But when you look at it from the 3D point of view, these planes are not in the same plane. Sorry, these rings are not in the same plane. If one of the rings is like this, the other ring is like this. Zinc, imagine that zinc is present here. Then if one of the rings is like this attached to zinc, the other ring is like this. They do not have a plane of symmetry. They are present in different planes. So, that is why tetrahedral complexes which contain bidentate ligands are optically active. Next, if in a complex the coordination number is 4, but the structure is square planar, not tetrahedral, I am talking about a square planar structure right now, the complex cannot be optically active. If you talk about a square planar structure, then all of the 4 ligands in the square planar structure, they lie in the same plane, okay, as well as the metal atom. The metal atom and all of the 4 ligands, they are in the same plane. So, if this is the square planar, okay, think this is my hand and it's a square. It's a square planar structure. The metal atom is present at the middle of my hand and the corners of my hand are where the ligands are present. Because they are present in the same plane, okay, even if the ligands are different, even if all the 4 ligands are different, I can still have a plane of symmetry coming like this, which is bisecting all the ligands, which is bisecting all the atoms, and it is making mirror images above and below the plane, right. If the ligands are same, then I will have many other planes of symmetry also. But if the ligands are different, all of the ligands are different, I am talking about the worst case scenario in which all of the ligands are different, then also that square planar complex is going to be optically inactive. Because why? Because it has a plane of symmetry going through this side.